kernels, images, and isomorphisms. So suppose we have a linear transformation usually we do Rm to Rn with an associated matrix A from Rm to Rn. And so we kind of want to get the sense that the columns of A are going to be the images of the standard bases. And so if we take a look at A1 up to AM, let me think, is that right? Yep. Just thinking about the indices, or the columns of A. So in other words, we could kind of write A as like A1 up to AM. And if this acts on any vector x, the image of this is going to be x1, a1, and then we're just going to add all of those together. So you can kind of think about it as, right, this is just a linear combination of our standard basis vectors. We have x1 times e1. And if we were just to pick out that piece of the vector, when this matrix acts on it, that e1 is going to pick out the first column of A. So times whatever scalar is being multiplied, we will have that component. So in other words, the image of Rn under the action of A, so sometimes we simply denote it A acting on all of Rn, A of all of Rn, or T of Rn, is given by the set of linear combinations So in other words, the span of the column vectors defines the image, defines the range. So that's what we call it. So i.e. the span of the column vectors of a linear transformation define the image or the range. So we have a few definitions. So we're going to let T be a linear transformation so V and W can be any arbitrary vector spaces. They don't have to actually be Rn or Rm. We will see, though, that any vector space of a given dimension is isomorphic to all vector spaces of the same dimensions. So we say T is injective. Book calls this one-to-one. If, for any two vectors, let's just use x and y, where the image of the two vectors is the same, we must have that the two vectors were the same to begin with. Namely, we cannot have two different vectors map to the same vector under the transformation T when T is injective. So we say T is onto or surjective if for any V, let's call it W, for any W in the target space. So we've seen that sometimes we have linear transformations. I can have a linear transformation from Rm to Rn, but sometimes the rank of that transformation, the rank of the matrix, isn't as large as it could be. And in this case, what's that mean? It means that we don't hit all of the vectors in the space we end up in, or the vector space spanned in the image isn't the full dimension of the vector space we land in. Onto says that it is. So surjective means any vector in the image space, in the target space, has some vector in the domain such that the image of that vector under the transformation maps to the given vector. So let's explore these concepts a little bit. Proposition. So suppose we have a matrix or a linear transformation, Rm to Rn. Linear transformation is injective. if and only if any vector set to 0 implies that that vector had to have been 0. So quick proof, maybe just a proof outline. We'll see how much we can get. So suppose A is injective. Then if A of x goes to the 0 vector, we also have that A of 0 goes to the 0 vector. In other words, A of x equals A of 0. And so by injectivity, so injectivity, I'll abbreviate INJ. This implies x equals 0. So that shows one direction. So to show the other direction, if AX equals 0 implies x equals 0, in other words, the only vector that a transformation sends to the 0 vector is the 0 vector itself, we want to show injectivity. Then suppose AV is equal to A times W for some vectors V and W. By linearity, this implies that AV minus AW should be 0. But by the linearity of A, this implies A acting on V minus W is equal to 0. And by our assumption, we have to have V minus W equal to 0. And hence, V is equal to W. So A is injective. So injectivity, this property that I can't send two different vectors to the same spot under a transformation. Transformation sends each vector to a unique vector in the image. It all comes down to how this linear transformation acts on what we'll end up calling the kernel. So we'll get to that in today's lecture. It's really the set of vectors that are sent to 0 that determine whether or not a matrix or whether a linear transformation is injective. Let's do one example. So suppose we have a transformation just from R2 to R2 where T of xy is given by a matrix and then the question, of course, is T injective or surjective or both or not either? So to check surjectivity, right? Surjectivity from our initial observation that the image of T or the range of T is determined by the span of the column vectors. So we've got 1, 1 and 1, 2. And what can we say about that? So since these are linearly independent, the range of T is equal to the entire vector space. So T is surjective. So that's another way of saying surjective, meaning that the range of the vector space is everything onto its image. Okay. So how do we check injectivity? By the previous proposition, we want to compute. You want to figure out what vectors are going to 0. And if we can show that the only vector that maps to 0 is itself the 0 vector, then we're good. We will have injectivity. So once again, we have a system of linear equations. How do we solve it? We can use a matrix. We can make an augmented matrix of our system. And when we row reduce, since we row reduce to the identity matrix, this essentially says that x has to be 0 and y has to be 0. So t of x equal 0 implies that entire vector was 0. So T is injective. Let's take a look at another example. So suppose we now have a linear transformation from R4 to R2, where T of ABCD is equal to A plus D and B plus C. And we want to take a look at the same things. Are we injective, surjective? One thing we should gather, that if we are mapping a higher dimensional space into a smaller dimensional space, then we cannot be one-to-one. We simply can't fit a 4-dimensional space into a 2-dimensional space without sending a lot of things to 0. So we kind of have to kill off a lot of dimensions, at least 2. So for example, if we want to check injectivity, we go through the same process. If we have T of A, B, C, D, we set it equal to 0. That's going to imply that A plus D and B plus C are both equal to 0. So in other words, here, we don't need parentheses there. So A is equal to minus D and B is equal to minus C. So for any vector that looks like A, minus A, B, and minus B, we will get a 0. And so we can pick, if we pick A and B to not be 0, we have a non-zero vector being sent to the 0 vector. So since we're killing off a certain non-zero vectors, T cannot be injective. For surjectivity, we want to be given any arbitrary vector in the image. And then what do we want? We want a vector in the domain such that, and That pen is done. I don't know if this one has much more. There we go. Such that this holds. So in other words, what we want is a vector that satisfies this. And now, there's going to give us a lot of different choices. So since we are not injective, there could be multiple vectors that map to this pair xy. It's easy enough to find a pair, so we could simply choose a equal to x, b equal to y, c equal to 0, and d equal to 0. Then t of x, y, 0, 0 is going to equal xy. So t is surjective. So there's going to be a theorem here. So suppose that we have a linear transformation T from Rm to Rn with the associated matrix A then T is injective if and only if the rank of A is M, T is surjective if and only if the rank of A is N. So remember, the rank of A of a matrix is going to be the dimension of the span of the row vectors, which is also going to be the dimension of the span of the column vectors. So what the rank tells us, we can determine the rank by coming up with a reduced row echelon form for the associated matrix. And when we find reduced row echelon forms, what are we looking for? We're looking for, in some sense, the number of rows of zeros at the bottom is going to kind of dictate the rank, because the non-zero rows will give us the rank of A. The number of zero rows, in some sense, are going to give us a notion of the null space, which is the dimension of the spaces that are killed off. And so we saw that if we don't kill off any dimensions, so if we're starting with an m-dimensional space and my image remains an m-dimensional space, then we're going to have full rank and we're going to be injective. Conversely, well, if we have that the rank of A is n, that can also be determined by the dimension of the column vectors. So the dimension of the column vectors, dimension of the row vectors actually are always going to be the same. And so if the dimension of the column vectors is n, well, we saw in the first setup that we looked at today that the dimension of the column vectors, or the span of the column vectors, determines the image of T. So if the span of the column vectors has dimension n, then it has to span the whole image space, meaning it's going to be surjective. Does that make sense? Okay, so I don't want to prove that guy. I just kind of wanted to talk about it a little bit. Let's see some more examples and maybe work through what's going to happen with compositions with these notions of surjective and injective. So for example, if we have T from Rk to Rm, and we have S from Rm to Rn, we can form their composition is, so here, let's write it down. So if both S and T are injective, then so is their composition. If T and S are surjective, and so is their composition. So taking a look at this and proving it, it's not terribly difficult. You can kind of just take a look at where the zero vector is going to go for injective. And I know that T is going to send the zero vector to 0 if it's injective. And so actually, maybe we should do this a little differently. Sorry, I'm setting that up a little bit. Of course, the composition, linear transformations are always going to send the zero vector to the zero vector. Really what we want to explore is if we have S composed T of X equal to 0, that's only going to happen when S of T of X is equal to 0. So if S is injective, that's going to imply that T of X had to have been 0. And if T was 0, or excuse me, t was injective, that implies that the x vector had to have been 0. Surjective, you can prove similarly. Maybe we'll just talk it out real quick. What's going on with surjectivity? Well, we have t. T is going to map rk to rm. And so if t is surjective, that means the image of t is going to cover all of rm. And so we're going to have all of rm now then feeding into s. And since s is also surjective and we have all of rm to start with, it's going to map all of that into all of rm. So surjectivity will hold under composition. So definition. A linear transformation that is both injective and surjective is called an isomorphism. And a proposition out of that. So suppose T, so any transformation between arbitrary vector spaces is an isomorphism. Then the inverse exists and is also an isomorphism. So isomorphism means structure preserving map, or like the same map. So it's kind of mapping one space to the same space. So any two spaces that are isomorphic, so we say two different spaces are isomorphic if we can come up with an isomorphism between them, namely a function that maps one to the other and is invertible. So I guess we should also include that as our proposition. So if we have a linear transformation and t is invertible, then t is an isomorphism. So if we can undo the operation, it had to have been an isomorphism. So to just kind of think about that for a little bit, if we are injective, that's saying that I can't map two different vectors to the same vector. Every vector that a transformation acts on goes to a unique vector. Surjective means I hit every vector in the space, the target space we care about. So why does that kind of give us this notion of being able to undo that operation? Think of the converse a little bit. So let's suppose I have like two different vectors that go to one vector. T of x. So just some ideas. If t of x equals t of y, and those two vectors are different, and let's say each of those, let's say it's equal to w in the target space, then how would we get an inverse. All right, we have this image in our target space of W, and I know two different vectors go to that. So if we need to undo the operation, and I started with W and took the inverse operation, we should end up back to where we started. But we have two different choices. We cannot define a well-defined function with two different choices for the image. So in order to invert something, we have to have injectivity. And so we can kind of think about surjectivity as well, because if we are not surjective, then we have W, some vectors in the image space, such that there is no vector. So T of X is never going to be W for any of the vectors in our domain. So if that were the case, how do we define an inverse? And again, we can't do it. So if there's specific vectors in the image space that, well, never were arrived at from this operation of T, well, there's no way I can invert that operation because nothing was acting on to get us to that target point anyway. So this is kind of the idea behind how to create inverses and why we necessarily need injectivity and surjectivity. So let's take a look at an example. So there's a couple ways to do this now. If we want to show that something is an isomorphism, we've got a few techniques now. Actually, here let's include some notation real quick on that page, just down at the bottom. So two vector spaces. Is this pen shot too? So if we have V and W vector spaces, then V is isomorphic to W if there exists an isomorphism between there. And of course, we can invert that as well. So we can essentially map back and forth between V and W in a unique way, or not necessarily unique map, but there is a map such that mapping back and forth will give us a unique association between the vectors in V and the vectors in W. And then we write. The book uses something a little different. The book uses like a similar symbol. So sometimes they'll write that. I like to use, I think more commonly we use like a congruent symbol. V is isomorphic to W. So let's take a look at an example. So suppose once again we have t from R2 to R2. Given by t of xy is x plus y and x minus y. And we want to show t is an isomorphism. So we have a couple ways to do that. We can demonstrate that t is injective and surjective. So kind of like we were checking in the last few examples. We can check injectivity by checking to see what happens if I have any two different pair of vectors and see if they can go to the same spot, or checking which vectors go to 0 will give us injectivity. And then for surjectivity, we just need to make sure that anything in R2 can be written in this format. Namely, there's going to be some vector that maps to it. But the other thing now we have is that linear transformations are invertible. And we learned yesterday that inverse of linear transformations are described by invertible matrices. So we can also come up with a matrix So what is the matrix associated with t? Well, what's t of 1, 0 going to be? It'll go to 1, 1. That'll be our first column. What's t of 0, 1 going to be? It'll be 1 minus 1. And so, of course, you can check that if that matrix acts on xy, we will get that exact transformation. And so what we can do is to check invertibility. Namely, we can row reduce. So subtract row 1 from row 2. And then, of course, divide row 2 by 2, negative 2, and then subtract that off from the row 1. So, of course, we did row operations here. We should be good about labeling our row operations. We did minus 1/2 row 2 to get that. And then we did minus row 2 plus row 1. So T inverse exists, which implies that T is an isomorphism. So these little arrows mean imply. So in terms of mathematical arguments, T inverse implies, T inverse exists, I guess we could write, which implies T is an isomorphism. All right, so some other ideas and theorems, lemmas, things we get. So lemma, so if T is an isomorphism, then T maps bases to bases. So just the idea of what's going on behind the scenes there. Well, we always start with the bases. And typically our basis we work with is our standard bases. And I know that the image is going to give us that respective column. Column J of T. So in some sense, since the columns of J have to be linearly independent, and that the rank of those has to be the same as the dimension of the spaces, then the number of linearly independent columns is the dimension, meaning that that set of column vectors, of linearly independent column vectors in T, is going to be the same dimension as the space. So in other words, our standard basis is certainly going to be mapped to another basis for the space. And then, as we saw yesterday, our change of bases matrices are invertible. So even if I start with one basis, I can always find a conversion into another basis. And so those are isomorphisms. And we should expect that to be, right? If we want to get the same space, a map from one space exactly into the same space, just changing the way it looks under a change of bases, well, we're getting the exact same space, and we're getting all of the vectors in that space in a unique way, according to the change of bases. And so, of course, these are both isomorphisms. And so if you can kind of think, well, if I start with any bases and then map it, and by the column vectors or understanding how it works with the standard bases, I know that the standard bases and the way T acts on that is going to give us a basis, because it's going to give us the set of column vectors in the image. And I know those column vectors have to be linearly independent and span the set. So they'll be a basis. And then I can just use change of bases to get any other bases in the image and the domain. And those are isomorphisms. So one thing to check, we talked about this with matrix multiplication, though. If S and T between two vector spaces are isomorphisms, and actually here, let's use Rn to itself, then so is S composed T. So a composition, if I apply an isomorphism, it's like we're going from one space to an exact copy of that same space. Maybe that same space lives somewhere else, but we are going to an exact copy of it under this transformation. Then if I map again from that space into another exact copy, well, we're still getting an exact copy. We just might live somewhere else in a bigger space. And naturally, as we learned with matrices, if we want to take the inverse, we just take the inverse of each of the transformations and reverse the order. So that's kind of the general idea in the way you can think about it. If we wanted to get a little more rigorous, we would want to be careful with our definition, because standard bases may not necessarily be the basis for V, especially if V lives in a bigger dimensional space. We got to be a little careful with that argument. But as we will kind of see in the next theorem, you can almost always think of your domain as Rn. Unless you're really trying to be fancy and have a subspace of Rn as your domain. You can. It just kind of adds an extra level, an extra layer of computations to do. But the ideas there are all solid. So the next theorem says that let U and V, or V and W, be vector spaces, subspaces of Rn. Then V is isomorphic to W if and only if they are the same dimension. So, of course, a corollary to that is if the dimension of some vector space is K, then V is isomorphic to R to the K. An easy way to kind of walk through the proof or the idea based off of what we were just talking about. If we pick a basis for V and likewise a basis for W, and we can define a transformation T from V to W by simply sending each basis element to the corresponding basis element of the other space. And then we do what's called extend by linearity. So in other words, we force, T has to be a linear transformation. We start with just defining how T behaves on the basis and then force T to be a linear map. So namely, T of any linear combination of these vectors is the linear combination of the image of the basis vectors. So since we're sending basis elements to basis elements, it's going to force injectivity. So namely, the only vector that can go to 0 has to be the 0 vector, and that's going to follow by the linear independence of the basis vectors we started with. So this vector can't be 0 because since we started with basis vectors and mapped them to basis vectors, it's going to force that the only vector that this transformation sends to 0 is the 0 vector. That gives us injectivity. Likewise, surjectivity, if I take any linear combination of the wi's, so any vector in the image space can be written as a linear combination of our wi's. Take that same linear combination of the vi's, and then T will map that to the image vector. So we'll get surjectivity as well. And of course, you can define invertibility quite easily the same way. Just map the basis vectors back, basis vectors for W back to the basis vectors for V. Okay, man, still got quite a bit to get through. I would like to get through a lot more of this theory so we can actually take a look at examples. There's kind of a corollary that the book lists to this theorem. I'll write it out real quick. I'll let you guys check that on your own. And it says the following are equivalent. For a transformation between two vector spaces that have the same dimension. So T is injective, T is surjective, T is an isomorphism. So if I know two vector spaces have the same dimension and I have a map between them, well, if we know T is an isomorphism, it's got to be injective and surjective. But now if I know the dimensions are the same and I have an injective map, you can kind of think of it in the sense that, well, if it's an injective map, we're not killing off any dimensions. That means the dimension of the image of T has to be the same as the dimension of W, meaning that the image of T is going to span all of W. So it has to be surjective. Conversely, if we are surjective, that means I have to have enough vectors to cover the image. I had to send to the image. And since the dimensions are the same, I have to use all of the vectors in V to cover the image of W. I can't collapse any two vectors into the same vector, or I can't send any more vectors to 0. Because if we did, we would kill off a dimension and then not cover the image space. So that's kind of the idea behind it. Take a look at the proof in the book. Let's see some examples, or do we want to just finish up with, we've got about 20 minutes. Let's finish up with the remainder of definitions and kind of the theory here. And then we'll start to take a look at a couple of examples. So just a few more definitions. I know this lecture's been a little rough, definitely more on the theory side of things. So hopefully you at least kind of understand the sense. You should just have an idea of what injectivity and surjectivity is, as well as what an isomorphism is. and why we get these invertible matrices, why both conditions are necessary for invertibility. So the last thing we want, so the kernel of a linear transformation is the vector space. So the kernel itself defines a vector space defined by we usually denote it kernel, K-E-R, of T, is going to be the set of all vectors in V such that T sends it to 0. So it's the set of all vectors that get mapped to the 0 vector. And I guess we should define our linear transformation somewhere. The image, I've been using this term a bit. Hopefully you kind of have a sense of it. It's like the range of T. Is defined by, usually we just say IM of T. And it's going to be the set of all vectors in W where T has some landing point. There exists some vector in the image, or in the domain, I should say, that maps to W. And the image itself, I should say, is a vector space. So the kernel and the image both define vector spaces. So I think the book actually lists that as a proposition. So proposition, the kernel of T and the image of T are subspaces, meaning they are closed under scalar operations, under linear combinations. So check that one in the book as well. Or if you want to see the proof, I can always help you work it out in office hours. Let's try to take a look at some examples, though. Actually, wait. 2 more theorems. Two more theorems. So proposition. So T is injective if and only if the kernel of T contains only one element, namely the 0 vector. And this should follow from our definition, right? Kernel of T is the vectors that T sends to 0. And so if T sends any non-trivial vector to 0, it's going to be killing off dimensions, which means it's not injective. And then our last theorem, this is a big theorem. We skipped the rank and nullity theorem. We didn't have time to do it when we were talking about matrices and talking about the rank of rows and everything, but it comes essentially down to the equivalence of this theorem. This is the rank and nullity theorem, namely that if T is a linear transformation between 2 vector spaces with the dimension of your domain is, let's say, K, then the dimension of the kernel of T plus the dimension of the image of T has to equal K. So you can think of this as the rank. And this is, we didn't define this, but this can be called the null space. The kernel, we could also call what's called the null space or the nullity. Null in the sense that it is the set of vectors. The kernel is the set of vectors that T just kills. It just sends them to zero. It's kind of killing that entire dimension, right? Because T is linear. The way you should kind of think about it is, let's say I have one vector here, and T is going to map that entire vector just to zero. It's not going to go to any other vector in the space. It's just going to go to a point and collapse that entire vector. But because of linearity, that means any other scalar combination of that vector, so that entire dimension that is defined by that vector, is going to go to that point. So it's going to kill off that entire dimension. So that's essentially what the kernel is. The kernel, you're taking a look at the dimensions, or you can, since the kernel is a vector space, we can find a basis for that vector space. And in many ways, those bases elements define the directional dimensions that T is just going to kill off. We're just collapsing all of those dimensions. They're all going to zero. Whereas conversely, if we take a look at the dimensions that T is not going to collapse, well, all of those dimensions that T is sort of maintaining, well, it's just going to morph and twist those. And that's where the image of T is going to be generated from. So the T does not kill a dimension. It's going to be somewhere, it's going to land somewhere in the image of a non-zero vector. And so we should kind of expect, well, if I have the dimension of the original vector space, the dimension of my domain is K, well, some of those dimensions we're going to kill off, and then some of those dimensions we're going to maintain. And so the dimensions that we maintain, those will end up in the image, and then the dimensions that we kill off, we'll keep track of those as the kernel. And then since that sort of expands, since that is the entire, all of the dimensions that we can have of V, the sum of those two dimensions has to be K. So that's the idea behind the rank and nullity theorem. And so to clarify a little bit, the rank and nullity theorem, I don't think this is called necessarily the rank and nullity theorem, but it is essentially the same idea. I think the specific rank and nullity theorem has to do with matrices. So if we were to take a look at a matrix, or the matrix representation of T, when we do these row reduction operations, we are in some sense, we're not modifying what the transformation is doing. We're kind of just modifying the bases and how the transformation looks under a change of bases by doing these row operations and maybe column operations. And so when you see a bunch of zero rows in a matrix, that is usually what's called your nullity. That will give you the dimension of how many vectors you're killing off. If you have zero rows after doing row reduction, it's kind of like saying those were the dimensions that we're just mapping to zero. And then the non-zero rows, as we've seen in terms of like solutions to systems of equations, those give us solutions to systems of equations. There are vectors that land in our image space and have a point in the image space that we can solve for. And so those dimensions end up being the dimensions of the image. And of course, since if we were to build a matrix out of that and do row reduction, either a row is going to be entirely zero or a row is going to have a one in it. We can write it in terms of our reduced row echelon forms with a one, and then maybe there's constants after that one that we can't get rid of, or maybe not. But in any case, the rows that are non-zero are going to give us a notion of the solutions we can come up with in the image space. And so that gives us our rank. Does that make sense? So again, I kind of wish we were in person so I could kind of see you guys and maybe draw some pictures a little bit better. That's the idea behind all of these: the kernel, the image, rank and nullity, injective, surjective. Let's try to see some examples and just work through a lot of this now. All right, so examples. So let's, V is R3, and W is going to be a subspace of R4, where W is going to be the span of 1, 2, 1, 1, 0, 1, 0, 1, 1, 1, 2, 0. So W we see is at most a three-dimensional subspace. And then we're going to have a linear transformation from R3 into W, where T of 1, 1, 0 is 1, 2, 1, 1, 1, and T of 0, 1, 1 is equal to 0, 1, 0, 1, and T 1, 1, 1 is equal to 1, 1, 2, 0. So things we want to understand: is T an isomorphism? And then maybe we want the matrix associated with T. So is T an isomorphism? Well, let's check. T, we know it's a linear combination, or it's only defined on 3 vectors, but it's a linear transformation. So we can do this process of extending linearly for T. So if we know how T acts on a basis element, or on a basis, we know how it's going to act on every vector in the vector space. So a few things we need to check: that the set we are acting on when we compute the span of this, what's going to happen? What are we going to get? Why should we get R3? Hopefully you can check or do maybe a row reduction of that matrix real quick to check that the span of those 3 vectors is all of R3. Namely, it's going to give us a basis because these vectors are going to be linearly independent. So certainly I can't take any combination of this guy is never going to reach this third, because we're never going to have a 0. Likewise here. And so to get any arbitrary coefficients, we actually need all 3 vectors. Check that on your own. Try to work it out. So we have a basis here for R3, a little bit of a different basis than our standard bases. We should also check that, and we can write it in a matrix maybe, 1, 2, 1, 0, 1, 0, 1, and 1, 1, 2, 0 are linearly independent. So right now, really what I'm checking is really the dimension. We have a map between two vector spaces. But first, the domain we know is 3 dimensions. The range is potentially 3 dimensions as long as these 3 vectors are linearly independent. So to check linearly independence, you would do some column operations or some row operations. I'll leave that to you guys. I don't know if there's a quick way we can get it. It'd be hard. You might have to go through the row reductions. So check that. But you should be able to find that they are linearly independent. And so we have a linear transformation now that's going to map bases elements to bases elements, right? If we are able to show that these are linearly independent, then that means the span of a linearly independent set, that linearly independent set is going to be the basis. So our W is a 3-dimensional space sitting in a 4-dimensional space. We know we have a map between them from a 3-dimensional space into the 3-dimensional space in the image. And moreover, it's going to map the basis elements, or it's going to map one linear independent set into the other linearly independent set. It's mapping a basis into a basis. So T is going to be an isomorphism. We can invert T simply by having T inverse send the basis in W back to the corresponding bases in V. Moreover, we can come up with a matrix representation of T. Now, here's where it's going to be a little weird because the matrix isn't going to be a square matrix, meaning the matrix itself isn't going to be invertible. But there's going to be a certain component of T that is invertible when only acting on the subspace in the image. So we know the matrix associated to T, it's going to behave exactly like T, meaning that when T acts on these vectors, and again, the nice thing about vectors is when we take a bunch of vectors, a set of vectors, and form them into a matrix, one of the interpretations of that matrix is just the span of those 3 vectors. In other words, this matrix, in some sense, can represent the vector space V. And so we have this transformation now acting on the entire vector space should give us the entire vector space of W. And in particular, the corresponding columns are going to be mapped to the corresponding columns in the image defined by the image of those image of those basis elements. Right? We could split this. We could have AT act on column 1, and we could show that that's going to be column 1 over here. AT act on column 2, that will give us column 2. Likewise, acting on the 3rd column will give us the 3rd column. So using it as a full matrix multiplication simply does all 3 of those operations in a nicer, conciser mathematical way. And so now if we know that we have a matrix AT acting on this 3x3 matrix to get this 4x3 matrix, all we have to do is compute the inverse. So our AT is going to be 1, 2, 1, 1, 0, 1, 0, 1, 1, 1, 2, 0 times the inverse of this matrix. So we need to compute that. And then multiply them. Any questions on that? So maybe we'll start with this calculation tomorrow and maybe a couple more of the examples that we didn't quite have time to get through today. And then let's see. So what else are we taking a look at tomorrow? Solutions to linear systems again. Yeah, good. So we'll kind of close off the full breadth of this theory of solutions to linear systems tomorrow. And then Friday, got another exam. So we'll have a brief introduction to determinants. Hopefully all of you guys have seen that somewhere in your K through 12 math classes. So starting Friday and then Monday and Tuesday of next week, we'll be taking a look at determinants, and we can actually rephrase a lot of the stuff that we've just talked about. These ideas of kernels, images, one-to-one, the rank, all that kind of stuff can actually be determined by determinants.